Motional EMF. Consider this. Let's say we had a conductor moving through a magnetic field. Now, as by definition, a conductor has free electrons, free charges, free to move. And say the conductor is moving at some velocity v, so all the charges on that conductor, all the electrons on that conductor are moving with a velocity v through a magnetic field B. So the electrons will feel a force, according to what we learned in chapter 29, QVB sine 90 degrees in this case. And hence, let's say if this conductor were moving, if this conductor were moving through this magnetic field like this, with the magnetic field going into the page like that, then with B cross B, that's going up, but then it's negative charges, so that force would be down. So all the negative charges on this conductor would be forced in a downward direction, thereby leaving behind a positive charge. So an opposite charge will build up, a positive charge will build up at the top of the conductor, negative charge at the bottom. And then eventually there will be an electric field that's built up so that the negative charge will be attracted to that positive charge. And at some point, that downward magnetic force will be balanced by the upward electric force. When that happens, when this moves through and the two forces are equal, then we'll find that QE will equal QVB. In other words, there will be an E field set up that is equal to the velocity of the conductor times the magnetic field. And with that E field set up, there will then be a voltage across the length of this conductor equal to the E field times the length, which will be BLV. Kind of like a BLT, only it's BLV. The induced EMF, the voltage, will be equal to BLV. Where B is the magnetic field, L is the length of the conductor, V is the velocity that it's moving with. If it's moving in the opposite direction, polarity of the voltage will be reversed, and we'll have positive on the bottom and negative on the top. Consider a similar situation where we have some rails and we have a conductor moving along these rails with a resistance over here. And so we have a closed circuit here. If this conductor is moving to the right here, then there's going to be a change in flux through this closed loop, this closed circuit, equal to the field times the change in area, which will be equal to the length of this conductor times the change in x, because that will be our change in area as far as a rectangle goes. Hence, we'll have induced voltage by Faraday's law equal to the change in flux per time, which will be the field times the length times the change in x per time. But the change in x per time is indeed the velocity of this conductor as it's going along the rails. So this voltage will equal BLV. Just the same way as just a free conductor moving through a magnetic field. If we put it on these rails, it will still generate the same voltage, BLV. And hence, if we have a resistance in this closed circuit, there will be an induced current equal to the voltage divided by the resistance, BLV divided by R. Since our flux, as you're looking at, the flux is into the page, and since the area is increasing, that flux is increasing into the page, this induced current will be will produce a field out of the page to oppose the increase in flux into the page, and hence this induced current will be counterclockwise by the right-hand rule. So we can model this free conductor moving to the right on these rails like a circuit with a voltage, an induced voltage, BLV, and the current moving counterclockwise through this resistance like this little circuit over here. The power dissipated in this circuit will be I squared R, which will be BLV over R squared times R, which will be B squared L squared V squared divided by R. And that will be the power dissipated in this moving conductor circuit. Let's try this out. In the figure, we're going to have a conductor moving to the right. Assume that R is equal to 6 ohms. The length of the conductor is 1.2 meters, and the magnetic field is 2.5 Tesla into the page. At what speed should this bar be moved in order to produce a current of 0.5 amps in the resistor? Well, we just proved that the current should be equal to the voltage divided by the resistance, BLV divided by R. So if we solve this for the velocity of that conductor, we have the velocity should equal the current times the resistance over the field times the length. And if we want to produce a 0.5 amp current, this will be 0.5 amps, 6 ohms over 2.5 Tesla times 1.2 meters. That will be equal to 1 meter per second. So if we move this conductor at 1 meter per second, we will produce a half amp current in that resistance. It's not going to be easy to move this across, though. This opposing flux and this opposing current is actually producing a force that is difficult, that's working against us as we're moving this to the right. So in order to produce this current, we're going to have to push on this in order to maintain that velocity. Here's a conceptual example of a moving conductor in a magnetic field. A spacecraft orbiting the Earth has a coil of wire in it. An astronaut measures a small current in this coil, although there's no battery connected to it, and there are no magnets on the spacecraft. What is causing the current? Well, you can probably see by my diagram, if you have a conductor moving through the Earth's magnetic field, you have a moving conductor moving through a magnetic field, and that would generate a voltage and a current. So that is one way that we could possibly steal some energy in order to create electricity. Always has to come from somewhere. So if we're stealing the energy from the Earth's magnetic field, we are stealing energy from the magnetic field, which is energy we might need because the Earth's magnetic field actually does something for us. It protects us from dangerous charged particles from outer space, namely from the sun and possibly from other places in the galaxy. So we can steal this energy, we just don't want to make it sure that we don't make it a major energy source because we might deplete the Earth's magnetic field. Here's another application. A railgun. Consider a high voltage power supply hooked up to a conducting system as shown. If we run a high voltage, we're going to have a very large current, and in this case, as we indicate here, it's going to flow clockwise through this circuit. As it's flowing clockwise, as you're looking at it, clockwise this way, that would produce a large magnetic field into the page. And hence, with this conductor moving to the right and the current moving down, with that current and magnetic field, there's going to be a force on that, pushing that to the right. Let's see, the current's going down, magnetic field on the page, force pushing this rail to the right. Let's say we reverse that voltage, and we have the high voltage going the opposite direction, so the current is going up through that rail, and we have a large magnetic field coming out of the page towards you. If the current's going up and the field's going out of the page towards you, this force is still going to the right. So whether we have a high voltage AC voltage, it doesn't matter which way it's going to force this rail to the right, and it's going to increase speed and accelerate and finally fling off the rails and possibly out into outer space. This is called a railgun, and NASA actually has tried to employ this idea because it involves no explosions. It's just a high voltage accelerating a rail in one direction. Maybe if someday we have to shoot nuclear waste into the sun, which is not a bad idea because the sun is a nuclear waste pile anyway, we need convenient way to do that and a safe way to do that, so that there's no rockets, no explosions. We could have a large railgun that could shoot things into space, and then that would be a consistent way to make sure our launch went successfully. We could also induce an EMF in a rotating bar. Consider this. We have a conducting bar of length L rotating with a constant angular speed omega about a pivot at one end, kind of like a helicopter blade. The uniform magnetic field is directed perpendicularly to the plane of rotation as in this figure. Find the EMF induced between the ends of the bar. Well, it's going to go around, and it's going to go around once every rotation. So it'll sweep out a total area of A, the area of that circle, pi L squared, in a time period t. So we would say that our flux by Faraday's law is going to equal the change in flux per time. And the field is constant, so that's going to be the field times the change in area per time. But we're going to go one full area of that circle in a time period t. So that's going to be the field times pi L squared, the area of that circle, pi r squared. And our t is going to be 2 pi over our angular frequency, because that's a period. 2 pi over the angular frequency. Pi's cancel out. And this will be equal to the field times the angular frequency times L squared divided by 2. That will be the EMF induced between the ends of the blade as it's going around. It's a function of its angular frequency. Let's try this out. A helicopter has blades with a length of 3 meters extending outward from a central hub and rotating at 2 revolutions per second. If the vertical component of the Earth's magnetic field is 50 microtesla at that point, what is the EMF induced between the blade tip and the center hub? Well, we just calculated a formula for this. Field times angular frequency, length of the blade squared over 2. Earth's magnetic field is 50 times 10 to the minus 6 Tesla. We have omega, which is 2 revolutions per second, but we want to switch that to radians per second. So it's going to be 2 pi radians per revolution times 2 will be our radians per second. And the length of the blade is 3 meters. So we have that squared over 2. We will generate a voltage of 2.83 times 10 to the minus 3 volts between the hub and the end of the blade. All right. Let's try another problem. Let's say we had a cloud with a lightning burst. A bolt of lightning passes 200 meters from a 100-turn coil oriented as shown. If the current in the lightning bolt falls from 6.02 megaamps to 0 in 10.5 microseconds, what is the average induced voltage in the coil? Treat the lightning bolt as a long vertical wire. So we have this long vertical current going down with 6 megaamps in 10.5 microseconds. Some distance away, 200 meters, we have a coil. It's a decent coil. It's 0.8 meters in radius. And there's going to be a magnetic field going through that coil. If the current's going down by the right-hand rule, there'll be a magnetic field coming out of the page towards you as you're looking at it. That'll be pretty much uniform over the area of that coil because we're kind of far away at that distance. So we can calculate the magnetic field at that distance due to a long wire. Mu naught I over 2 pi r. Mu naught is 4 pi times 10 to the minus 7. We have 6.02 times 10 to the 6 amps. And 2 pi, we're 200 meters away. So that field is 6.02 times 10 to the minus 3 Tesla. Hence, the EMF is going to equal the number of turns, change in flux per time. We have a 100-turn wire. The area of this loop is pi times the radius squared, pi times 0.8 meters squared. And we're going to go from 6 megaamps down to 0 in 10.5 microseconds, giving us a voltage of 1.15 times 10 to the 5 volts. 115,000 volts. This gives you an idea that if there was some way where we can consistently know where lightning was going to strike, we could set up these coils and try to steal energy from that lightning bolt. By inducing voltage in these coils, 115,000 volts would be very useful to have if we could have a consistent way of utilizing the lightning bolts. That's something for you as an engineer to think about in the future. The EMF for any closed path may be expressed as an integral of a closed path of an E field over that path, kind of like what we did with Ampere's law. And this is really the true form of Faraday's law. In Faraday's law, we just thought of it as being an EMF already within a closed circuit, but this could be a free E field out there as well, being induced by a changing magnetic field. So this electric field can be a non-conservative time-varying field generated by a changing magnetic field. Consider this device. We have ourselves two magnets, a north pole and a south pole, and between the north pole and south pole is a large magnetic field, and we have a coil between these two poles, and we have a crank on this coil, and if I were to turn this crank, I would be changing the flux through this coil, and by changing the flux, I would induce a current to flow, and hence I would induce and have electricity. So that's the basic idea behind generating electricity. If I were to turn this coil in a large magnetic field, I would generate electricity. So what's to stop me from giving this crank a good kick, have it start spinning, and then just put that coil in the magnetic field and generate electricity forever and ever for all of our needs? Sounds pretty good. The problem is trying to keep that thing turning. Let's say I had really the best ball bearings around, and this thing had no friction, and it would turn and turn and turn, except for the fact that when we're generating the electricity, the induced flux and the induced EMF is in reaction to the changing EMF that is going on. In other words, it is opposing the change. So every time that we have this coil going through, creating a change in flux, we're inducing a current, causing a torque on that coil that is opposing the change. In other words, it's hard to turn this coil because this torque is going in the opposite direction. So as I'm turning this crank, it's hard to turn this crank in order to generate that electricity. It's hard to do. Another way to look at it is by conservation of energy, the first law of thermodynamics. You can't get something for nothing. So if I'm generating electricity, it has to come from somewhere, and it's coming from me turning this crank. So the physical motion of turning this crank, me breaking down chemical energy and trying to extend that energy mechanically on this crank, is what's ultimately generating that electricity. So you can't get something for nothing. The way we generate this electricity then in power plants is, for instance, in the hydroelectric power plant, we would have water go over and fall at a certain distance mechanically, so it has kinetic energy at the bottom, and that hits a turbine, and the turbine turns, and that turns the coil within a large magnetic field and generates the electricity. So that's the way it's done in a hydroelectric plant. So we're basically converting the potential energy of the water eventually into the electrical energy of the electricity. How you would do it in a coal-burning power plant is you would burn coal and you would heat water and generate steam, and the pressurized steam would turn a turbine, turn a coil in a magnetic field, and generate electricity that way. So you basically heat the coal to turn water into steam, pressurized steam, use the steam to turn the turbine. Doesn't sound very efficient, but that's the way it works. How would you do it in a nuclear power plant? In a nuclear power plant, you would have a nuclear reaction, which heats water into steam, pressurized steam, which turns a turbine, which turns that coil in a magnetic field, generates electricity. Basically the same idea as a coal burning power plant, only you only use the nuclear reaction to generate your steam instead of the coal. Again, not very efficient, but that's our design of our power plants currently today. If this loop rotates with the angular speed omega, we have a generator, and the voltage of that generator will equal the number of turns, the field times the area, NBA, omega, sine omega t. We will generate a sinusoidal voltage. And if there's resistance there, it'll be a sinusoidal current with a maximum value equal to NBA omega. So this current will alternate. So it'll be positive, negative, positive, negative. That's the kind of voltage we're going to generate. That's the kind of current we're going to generate with this kind of coil device. If we want a DC generator, we might put two gaps in our contacts there. So as we're going positive with our sinusoidal function, we're just about to go negative, then we kind of reverse the leads by going over those gaps, and both leads will change, and hence what was going to be negative all of a sudden becomes positive again, and we go positive again, and then as we're about to go negative again, we reverse the leads again by the action of those two gaps, and then it goes positive again. So we rectify everything in a positive way, so it looks something like this. If we add a bunch of these signals, all of them rectified in positive form, then we add them all together, all of them generally out of phase, we end up with a net constant voltage after a while, and that would be our DC voltage, the superimposed result of all those signals. Motors. A motor is basically an electrical generator in reverse. If we run current into the coil of the motor, that will cause it to have a torque, and it will start turning mechanically, and that will give us the action that we want for the motor. So we're going to convert electrical energy into mechanical energy of the motor. A generator in reverse. The current is supplying the torque, mechanical torque, that will allow us to do work. In these chapters, from chapter 23 up to now, we have secretly introduced to you Maxwell's wonderful equations. The first one, the integral of an E field through a closed area is equal to the charge enclosed over epsilon naught, you recognize as Gauss's law. And that is actually one of Maxwell's equations. He kind of adopted that into the equations that we need. There's also Gauss's law for magnetism. The integral of a B field over a closed surface is equal to 0, basically stating that there are no such things as monopoles, magnetic monopoles. You can't enclose a North Pole or a South Pole by themselves. We also have Faraday's law, and this is the longer form of Faraday's law that we were just talking about, where we have an E field dotted over a path length, and that is a voltage, and that is equal to the negative magnetic flux per time. So we have an E field generated by a changing magnetic field. Faraday's law. Here's the Ampere-Maxwell law. We know Ampere's law. The integral of a B field over a path is equal to mu naught times the current enclosed. But in order to account for a chance that you might have a change in E field generating a magnetic field, we have an extra term that we'll explain in Physics 3, but it's equal to negative epsilon naught mu naught change in the electric field per time. So we can change the electric field and generate a magnetic field as well, and that is the Maxwell contribution to this law. And sometimes we have a fifth law that is included as one of these Maxwell's equations called the Lorentz force. It is simply the force on a charge moving in either an electric field and or a magnetic field. And it's QE plus QV cross B, which we've looked at the separate aspects of that for electric and magnetic fields. So these 5 wonderful equations explain all electromagnetic phenomena and included in that is the study of light. So this is sometimes regarded as one of the greatest contributions, the greatest simulation of equations in theoretical science. Maxwell's wonderful equations that you now know and love. It's even beautiful, more beautiful, if you introduce some mathematical operations here, like the curl and the divergence. It makes these equations look very, very simple under those operations of curl and divergence. They're simply simple and beautiful. Let's conclude this lecture on chapter 31 with what we call eddy currents. Consider a conductor made out of, say, copper, or in this case aluminum, and it has no magnetic material in it. It's simply a conductor that has free electrons. However, if this conductor moves in a magnetic field, those free electrons are going to move, and they're going to generate voltages and currents, as we've been talking about. So as this conductor moves into a magnetic field, we will have a current that will start to move circularly in this conductor. And because that current is moving, as we look at this conductor, this moving up here, with it moving up and a field going into the page, there'll be a force against the motion of the conductor that will start to slow it down as it moves into this magnetic field. If it tries to escape this magnetic field, the current will flow in the opposite direction due to the forces on the charges. And as the current is moving up and going out of this field, there again will be a force against the motion, slowing it down. So even though this is not magnetic material, it's a conducting material, as it moves into a magnetic field, it sets up these currents, which have magnetic moments themselves, and they will slow down this material. So it looks something like this. Let's see if I can set this up. Here's a magnet with opposite poles, and as I move this conductor tends to stop. I have to actually force it through there in order to get it through there. So that is eddy currents, and that's caused by the currents moving through this free conductor. Note, however, if I take another aluminum piece and I cut slots into it, so the large eddy currents can't flow, because now there's no conducting material down here to allow those currents to flow. That's going to interrupt the possibility of those eddy currents through this, and it goes freely through without being stopped. How about that? Well, if I cut slots into the conductor but allow a strip of conducting material at the bottom, so these large circular eddy currents are allowed to move, then those eddy currents will slow it down again, and it'll break. So with the free slots, large eddy currents gone, it only slows down slightly, but with the large eddy currents allowed to move, it slows down again. That's the best I can do as far as demonstrating that in front of the camera here. But that's a cool thing about induction and induction brakes on a conducting material. So that concludes chapter 31 on inductance and induced voltage.